What we're going to start with 6.2 is what are called Riemann sums. And what's happening here is it's a graphical approach to setting up a definite integral, which the integral is a new term for you, but I might as well just give it away. What is so awesome and great about calculus is the premise of the antiderivative that we just did in section 1 is actually setting us up to find the integral, which is actually the same symbol, dx. And what it's going to represent is the area under a curve. And I'll let you pause the video, or you can just stop and rewrite or read this and understand that what we're doing is we're going to use Riemann sums to estimate the area under a curve. And the main premise with this is that we're going to set up rectangles somewhere in a curve. Okay, so we're going to do a lot of these, so hopefully you get good practice. So the way we write this problem is we're going to approximate the area under the curve between x equals 1. So right here's x equals 1. So they nicely gave you the graph already. And x equals 7. And you're going to want a calculator for this, which I just, where I'm recording this, I don't have a calculator. So I'm going to go to the answer key fairly often. But I'm going to give you the visual, so don't worry. And the whole premise of this, and we're starting with a left Riemann sum, is we're going to make several rectangles underneath the curve to approximate the area. Now, the notation that we're going to get used to is we're going to say, we'll write it as the integral from 1 to 7. I know this is the antiderivative sign that you've seen of the function f of x dx is about. Okay, so get used to me writing it that way. And we're using this function. And as you reread the problem, we want the left Riemann sums with a width of 2 units. Now I know he says length, but I would say width. So as we establish where our bounds are, our lower bound and our upper bound, 1 is our lower, 7 is our upper, and think about, well, if we want a width of 2, so the next part of the rectangle that I care about is at x equals 3. And then after x equals 3, the next one we care about is x equals 5. And then we go to x equals 7. So where does the left come into play? Is between the 1 and the 3, we care about the height of the function on the left side, and we end our rectangle. So hopefully you see the rectangle there, which has a width of 2, and then a height of, looks like it's about 6 point, I don't know what, but you can figure it out by doing f of 2. And that's what I meant earlier when I said like using a calculator to plug in 2 and for x squared to be 4, so -4/3 plus 4 plus 5. And notice that I'm doing the area of a rectangle formula, width times height. Now that only gives me this approximation. So maybe what I should have done is set it up with multiple colors. So I'll just change colors. And then we're going to add to it the next rectangle. So the rectangle from 3 to 5, again, has a width of 2. And then what height are we going to use? Well, because it's a left Riemann sum, we're going to use the left side's height. Oh, whoops, I did f of 1. I'm sorry, I messed it up already. This should have said f of 1. I'm sorry. I don't know what I was thinking. And so between 3 and 5, the left one is f of 3. And even though I made a mistake here, I'm going to go to the answer key and you'll see the right one. and then plus the, oh, I should have color coded that. That'll find us this area, and then plus the last rectangle, because we're looking from 5 to 7. Well, the height of the 5 looks like it's up here, and that'll give me this area, 2 times f of 5. So as we look at this, notice that we miss some piece that's an area that would be under the curve, but then we go over approximations a little bit later. And so that's why it's an approximation. We know it's an approximation. So as promised, I'm going to go to the answer key, although the answer key is sideways. And there we go. So this is correct. You might need to tilt your head. Actually, I should just edit this BD and rotate it. There we go. So as you're looking at this, notice that the author also factored out a 2 out of each of these and used this calculator to figure out this. So notice he even emphasized that there's a bit of an over approximation on these ones, but that's to make up for this under approximation for that one. All right. And notice he even points out, although the antiderivative and the indefinite integral are actually synonyms. They're slightly different. I wouldn't actually classify them as synonyms. Some people identify an integral as an operation. Sorry, I said that backwards. The antiderivative as performing an operation, whereas the integral is a slightly different thing. But anyway, so notice the answer here, 42.6 repeating. Okay, so I'm going to move forward. Notice what happens if we change the width of each rectangle to be 1 unit. So there's a lot of things to consider. It's still a left Riemann sum though. So as you notice, my width is now going to be different. But as I have more rectangles in here, what do you think is going to happen to my approximation? Because I won't have nearly as many under approximations, and I won't have nearly as many over approximations. But it looks like my area under the curve will be a better approximation. Now, how's the formula going to be written? Well, each width now is 1 times f of 1, the height of the first rectangle, plus 1. I'm going to be done writing 1 times because that's not going to change anything. But notice it is length, width times height, and the width is 1 throughout all of these. So basically, the area under the curve is going to be all of these values. And notice that I'm not including f of 7. Well, why not? Well, f of 7 only happens on the very last rectangle, and it's on the right side of the last rectangle, which is not included on the left-hand Riemann sum. So I just wanted to point that out before I show you the answer key, which I will do, and I will rotate it so you can actually see. There we go. So note even color code, the pink is an under approximation because we're missing those pieces, but these orange are over approximations, but we get a better answer. So what happens if we have, we make our rectangles even smaller, is we get a better approximation. And notice he factored out a 1/2, kind of like what he did on the first video. Yeah, so the whole premise of this is, and why is this calculus, is because the more rectangles that you have, the better approximation. Well, how many rectangles would it take? How about the limit as n goes to infinity? The limit as n goes to infinity of all of these rectangles. The more rectangles you have, the best the approximation. All right. I was just sneaking ahead. I should have known already that the next one's going to be right Riemann sum. But the right Riemann sum is not really any different. How about that? I'll just go to the next one. So I have confidence you guys are all smart enough you can figure this out. The only difference for the right Riemann sum is when you're given the choice between the left side of the rectangle or the right side, you choose the right side to go up to the height. It will give you a different approximation. So notice the width of 2 is pretty poor because we have an overestimate, pretty quickly. And then there's a lot of underestimate. We are missing a lot of piece here that we didn't account for. But notice the math, 2 times f of 3. So width is 2, the height is we're using the y coordinate when x equals 3. 2 times the width, f of 5, the y coordinate, and then plus 2 times f of 7, the y coordinate there. Notice the poorly under approximation. And then the same thing with the next one. All right. Here's one more. Let me rotate this so you can actually see it. I should have done this ahead of time, but you guys can forgive me. There's another right Riemann, and the more rectangles you get, the better the approximation. And feel free to ask, reach out to me and ask for help if you need it. Okay, if you're still struggling with these ideas. Okay, and this is exactly what he's saying. As the width of the rectangles decrease, okay, so the more rectangles that you have, the less overage, underage, I like that phrase, which means you're going to get a better approximation. You're going to get closer and closer to the actual area. How many rectangles will it take? Infinity. If we get infinitely small rectangles, widths of rectangles, I should say it that way, we'll get an exact area, actually. And before ending this video, I do want to at least touch base on the midpoint Riemann sum. Because what do you do with midpoint? And I'm really emphasizing it here because I used to do this wrong. Okay, so between, it's a width of 2. I don't like that it uses length because I think of this as a width. But what you use is the midpoint of 1 and 3. So what's halfway between 1 and 3? That's x equals 2. So you go to that y coordinate. Okay, it's not halfway between the two y coordinates. It's halfway between the x's, and then you do, so halfway between 1 and 3 is 2. If you want to, you could actually add, do the midpoint formula, and then times 2. And then same thing goes for the next one. Halfway between, the width is still 2, times halfway between 3 and 5, and that y coordinate. So then f of 6 for the last one. And some would argue that the midpoint midpoint Riemann sum is a better approximation than doing a left Riemann sum or a right Riemann sum. And I would just say, it's up to the equation, really. Because as I go, like I said, I'm going to show you the answer key. Flip it so you can actually see it. Notice that it's the y coordinate at the midpoint between 1 and 3. So x is 2. So 2 times f of 2 plus 2 times f of 4. 4 is the midpoint of 3 and 5. And then 2 times f of 6, the midpoint of 5 and 7. And you get an approximation. I'm not going to say it's better or worse. I'm just going to say you get an approximation. And likewise with this one, because now it's widths of 1. And any one of these could show up on an AP exam. And I'll pick it up right after this video for the second one.